Well, hello there, and welcome to these video notes for chemistry on Learning Target 4.6. In Learning Target 4.6, we are going to describe how the periodic table is arranged based on electron configurations. We are going to understand and know how electron configurations change and stay the same as you move both down a family or group and across a period on the table. And we're going to explain why elements in the same group or family have similar properties. And you can also find additional information on this learning target in your book, section 6.2. So here we go. Here is a periodic table, and you have a blank one in your notes as well. And what we'd like to do first here is look at these in terms of what we call blocks. Now, on your giant periodic table, we took some time to write in the last term of the electron configuration, and what we found, and what you should have written down when you did your using the giant periodic table in your groups, is that everyone in this family ended in NS1 and everyone in this family ended in NS2, which means all of these elements in these two families end in S something, S1 or S2. So that represents what we call the S block. So that should be in your notes. If not, go ahead and draw it in. And if you were in my class, we color-coded all those elements as having a black card. Over here then, we saw that we had the elements P1, NP1, NP2, NP3, NP4, NP5, and NP6, with the exception of helium. Helium was 1s2. So we colored all of those elements green, and because they all ended in P something, P1 through P6, we called those green elements the P block. Then we took blue, and we saw that all of these elements ended in D something, ND1, ND2, ND3, ND4, ND5, ND6, ND7, ND8, ND9, and ND10. So N is just a number, some kind of a number. And we colored all of those blue, and since they all ended in D, we called these the D block. And then finally, in orange, get my orange here, we labeled these F1 all the way up through F14, and those were all ending in F something, so we called this the F block. So now we have ranges of our periodic table that correspond to exactly how many electrons can be held in a sublevel. S block has 2 families. S can hold 2 electrons. P has 6 families. P has 3 orbitals, which means a total of 6 electrons. D's have 5 orbitals for a total of 10 electrons, and F has 7, total of 14. So that comes right from your atomic orbital chart. So now we have these by block. And I have another picture here. This is the same kind of deal. We've got our S, P, D, and F block. We've got S1, S2, P1 through P6, D1 through D10, and F1 through F14, but now we've got valence electrons too. So one thing that I want you to go ahead and label both on your periodic table in your notes and on your periodic table that you actually have, your reference sheet, is the number of valence electrons. And the pattern that we saw in your giant periodic table looked like this. 1 valence electrons, 2 valence electrons, 3, 4, 5, 6, 7, and 8. So what I like to do is say 1, 2, skip a few, 3, 4, 5, 6, 7, 8 valence electrons. The exception to that is helium, which got moved over here because it has 2 valence electrons and ends in S2. Your periodic table has it here. The reason that helium is here on your periodic table is because it is considered a part of the noble gas family, as it is very stable. All right, so we noticed that all of the D block and all of the F block have 2 valence electrons as well. So it goes 1, 2, all of these have 2. All of your inner transitions that go in here between the S and the D have 2. And then 3, 4, 5, 6, 7, 8. So just by knowing where an element is on the periodic table, we can predict how many valence electrons that element has. And valence electrons, remember, are the only ones that do anything interesting. So if we know how many valence electrons there are, we will know how an element behaves itself. So all elements in the same family have the same number of valence electrons. So, when we say the alkali metals, group 1, are very reactive, they're very reactive because they all have one valence electron, which makes them very reactive. So that having one valence electron is the thing that they have in common to make them very reactive. On the same kind of idea, noble gases are very unreactive, and that's because they all, with the exception of helium, have 8 valence electrons, which makes them very stable. So it's the valence electrons being the same that gives them that feature. Remember that periods are your horizontal rows on the periodic table, and there are 7. So if I were going to number the periods, I would number them going down 1, that's period 1, period 2, period 3, period 4, period 5, period 6, and period 7. These two series go up into period 6 and 7. They're squeezed in there, so they are part of period 6 and 7. Families or groups are the vertical columns. There are 18. Hopefully at this point that is a very familiar concept. Okay, this is where we get into the nitty-gritty of 4-6. What we need to know is to be able to find an element on the periodic table based on its electron configuration. So what we need to know is the period and group, so we can kind of play battleship with where an element is on the periodic table. So the first thing we're going to talk about the period. The period that an element is in, so the horizontal row, is the same as the S energy level, or where the valence electrons are. So if I have this example here, which is cesium, here is the kernel notation for cesium, and remember, in a kernel notation, the valence electrons are always visible. So my valence electrons are in the 6th energy level. It's also corresponding to S. So because the valence electrons are in the 6th energy level, that means cesium is in the 6th period. And if you look on your periodic table, cesium is number 55, and it is indeed in the 6th period. I would like for you to try another one. Okay, so in this particular example, remember, find your valence electrons. That's going to tell you what period it's in. So when I find my valence electrons are here in the 3rd energy level, which means this element is in the 3rd period. And with 2, 4, 10, 12, 16 electrons, that's sulfur. And sulfur, if you look, number 16, is indeed in the 3rd period. To find an element, though, we need more than just the period. We also need to know what group or family it's in to narrow it down. So we can do that by finding the last sublevel, which is another thing that you did on the periodic table. So we organize these based on the sublevel of the last term in their electron configuration. So if you look at this, rhodium, right off the bat, we can tell, whoops, I don't know why I did that. Rhodium, here's its electron configuration, not sure where there's a comma there. Its electron configuration is in kernel notation, krypton 5s2 47. So right off the bat, from that electron configuration, I can tell that rhodium is in the 5th period because its valence electrons are in the 5th energy level. So rhodium should be in the 5th period. However, its last term is 4d7, which means if I look at my periodic table, and I'm just going to sketch a quick one right here. It's a pretty good sketch. If I look at my last term, that tells me what group it's going to be. So that tells me 4d7 means that it's going to be in the D block, which is here, and it's going to be 1, 2, 3, 4, 5, 6 in the 7th family, or the one that ends in D7. So we count over from D1, D2, D3, D4, D5, D6, D7. So it's going to be in this family, and in the 5th period, 1, 2, 3, 4, 5. So if I look, I should find rhodium right there. So D7, 7th over, and then the 5th period down. Now notice, this is actually family 9, because even though it's D7, there's S1 and S2. So if you include those, plus 7 in the D, we're actually in family 9. So let's do another one real quickly. I want you to tell me what period and family an element with this electron configuration would have. Let's see. Xenon. Oh goodness, I picked a big one. 4F14, 5D10, 6P1. Okay. So try that one, pause it, and when you get done, let's see what you got. All right, so for period, remember that's valence electrons. So my valence electrons are in the 6th energy level, which means this should be in the 6th period. So that's easy. And then my last term, right here, tells me that it should be in the P block. So here's your P block, and it should be the first family in the P block, because that's P1 all the way up through P6. So that is actually family 13. So first in P block, because the P block is 13 through 18. So that's family 13, 6th period, which gives me TL number 81. So that's my element. So it's kind of nifty. The more you get used to this, the better you do at it. So you just keep quizzing yourselves on periods and families or groups. And we use the periodic table to help us figure out electron configurations. Oh, and look at all that stuff that I wrote that's already there. Well, that's it for now. Have a wonderful day, and I will talk to you later.